enjoyable No Count Friday. Hope that worked for you. It was mentally healing. It's pretty good for me, not bad. I want to kind of start off, I went to look and see how the web work was going. It's going for some. I know that much. So I kind of wanted to talk, there's one of the problems on there I have to go in and grade, so I need to go in and look at it for you. And some folks have started this, and a couple folks have got it down, but there is a little confusion I can see in there. So I wanted to talk about it, and it's also a great way to talk about what we did right before we took our extended vacay over the weekend. So it's kind of like this. It's something along the lines of I've got a velocity curve with respect to time. Looks something like this. And they're cutting the interval from 0 to 2 into n equals 4 subintervals. And I'm kind of emphasizing that n on there because I'm going to push forward with that idea that n is the number of cuts that I've made, the number of rectangles I've got in there. And they give you 3 different versions of this graph. The first one on each of the subintervals uses the left endpoint for the height of the rectangle. The second one uses the midpoint, the exact midpoint of each of those for the height of the rectangle. And then the final one is using the right endpoint of each subinterval for the rectangles. So let's take a look at how we could do this. Let's kind of go through quickly. I'm not going to do the exact computation, but I'm going to show you what you need to do. I honestly didn't write down what it was, and it probably changes a little bit for each person. So let's say I'm doing the left endpoint. And what this left, mid, and right is, this is what determines the height of the rectangle. So if we're going to do the left endpoint, and I've got n equals 4, I'm going to cut this interval into 4 pieces. I'm going to go to the left end of each and go up to the function. Is that adding? Okay, good. Nice. And I'm going to go up to the function to determine the height. So for this one, notice that I use t equals 0. And then for this one here, I'm going to use t equals 1/2. You kind of got to estimate, right? They don't give you all the points. And I'm going to use t equals 1/2. And then I'm going to use t equals 1 for this guy. And then lastly, I'm going to use t equals 1.5 for this guy. I get a picture. They give you the picture, but that's how the picture is achieved, using those left endpoints. So your job is to add up the areas of all these rectangles. And I think that some of the confusion is coming in maybe in knowing how to determine the exact heights. Don't estimate the height of the rectangles. And I think that was the problem in at least a couple cases, where folks were like, looking over here, trying to figure out what the height was based on this, and you're not going to get it. It's kind of, they're weird heights. So for this left endpoint rule, let's call this area 1, area 2, area 3, and area 4. What is that going to look like? Well, it's going to be the height of the rectangle times the width of the rectangle. So here, the height is going to be v at 0 times the width of the rectangle. That's constant. That's not going to always be constant. I'm going to switch that up today. But on this problem, those widths are always the same. So times 0.5. So that's height times base. Height times base. And then I go, and you have to figure out, what is v of 0? What is the next rectangle? It's v of 0.5 high times its width of 0.5. And once you get the rhythm, you just grab each of those. 0.5 plus, and you'll literally have to crank that out and get that number. That's your answer right there for that one. So just a little bit of computation is all it's going to take. If you know how to use Excel, you can make this really easy. If you got any Excel skills, totally. You got no Excel skills? You got some. A little bit. Excel could make this kind of thing really lovely. Okay, midpoint, where things started getting a little weird. Instead of using the left endpoint, I'm going to find the middle endpoint, or the midpoint of each of the 4 sub-intervals. And here you gotta grab this point right here, which is 0.25, and use that as your rectangle height. And then what's between these two? 0.75. Use that. And then we've got 1.25. That's the next height I'm going to use. And then lastly, last one's 1.7. Now what's going to change between these answers is what I'm using to evaluate V. The only thing that's going to change is where you're evaluating V. So for the next one, for the midpoint, it's going to be V at 0.25 times a half, plus V at 0.75 times a half. All down the way until you get to, well, I'm just skipping one here. I'm going to leave a little bit for you to do in there. Plus V at, that last one is 1.75 times 0.5. Knock that one out. The bottom one is, now use the right endpoint. So instead of 0, 1/2, 1, 1/2, I'm going to use 1. What am I going to use, Tim? Wait, so
you use 1/2, right?
Yes, I use 1/2. Yes, sir.
1 and then 1.5 and 2.
Exactly. So you just kind of shift everything. So here it's going to start at V of 0.5 times a half. V at, what's the next one? Is it 1?
1.
Yeah, thank you. Plus V at 1 times a half, and on down the way. And your last one, of course, is going to be V at 2 times a half. Use your calculator, get those precise answers, round to like 2 decimal places of accuracy, you'll get it. Does that sound good? Let's try to like start this before Wednesday if we haven't started this problem set. It's not, it's, folks who have done it, was pretty chill? Or was it a lot of work? It's not too bad because you can use the calculator, right? You can go to the website and make this all easy, and you should do that. This is the only one you really kind of have to do by hand. And maybe if you were being a little bit clever about it, you might be able to use the calculator on it too. Just saying. Always ways. Anything I can help you with on that web work? Let's try to get that sucker done by Wednesday. Good. Okay. All right. I want to kind of take this idea. So we had this idea that given a velocity curve, we can find the area. And I'm going to write this a little bit differently because I'm going to extend the idea for it. Between the curve and the x-axis and the t-axis. So, given a velocity curve, we can find the area between the curve and the t-axis to get the, it's not exactly distance, but let's say displacement, which is a little bit different. Kind of the same, it can be the same. But displacement could also be, oh, I moved forward 3 and back 2, so my net displacement was 1. Does that make sense? Was that a question? Did somebody say something, or am I hallucinating? Somebody did say something. Okay. Cool. Thanks, Sasha. So for example, here's one example. We have a net displacement of whatever this was. The problem is you don't know where you started. It's just telling you that if I start somewhere and I move at this velocity, then the change in my distance will be this sum right here. What if I had a velocity curve that looked like this? Let's just look at that for a minute. So let's say this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's my velocity curve. So what is this particle doing if it has this velocity? And let's think of the area between the curve and the t-axis. And I'm going to change this idea of area to something called sine area. So what do I mean by that? That means if I'm above the horizontal axis, this is positive area. And if I'm underneath, that's a negative area. So this is like positive displacement and negative displacement. So think about this. If this is my velocity, I start off going really fast, but my velocity moves to 0 within the first second. So within the first second, this thing actually comes to a stop. It's going super fast and slowing down and stopping at the 1 second mark. And then what happens? It starts to have negative velocity. What does negative velocity mean? Moving backwards. So this up here is moving forwards. And this down here, this region, is moving backwards. So what is the net displacement here? Well, we don't have yet the skills to do this, and I didn't give us a formula for V of t, but do you think this thing's net displacement, so let's say it starts right here, here's our particle. Do you think this particle ends up to the left of its original position or to the right of its original position? To the left. It looks like, can you see that this area here is a little bit bigger than this one, actually significantly bigger? So this negative displacement is bigger than this one. So this particle, its motion is probably like this. Rocketing forward, so here's t equals 0. Rockets forward, slows down to 0, and this is at t equals 1. The particle stops. Yeah, that's good information, bro. Thank you. Very loud. You must work at American Eagle. Okay, and then from here, I start moving backwards, and I slowly accelerate. So I start at 0 velocity, and then like around 3.5 seconds, I'm at max velocity negative. So rockets back. And keeps moving backwards, but slowing down until at 5 seconds, it's got a 0 velocity. So here at t equals 5, we stop after moving in reverse. But the change from here to here, the net change, remember what we did? We started here, and then we moved here, and then we came back here. If I took the sum of those two areas, so let's call this area 1 and area 2, area 1 plus area 2 is this point right here. It's your final displacement. It's actually, sorry, area 1 plus area 2 is this distance right here. And that is my net displacement. Even though I did travel forward, I'm just looking at the final change after the process is complete. But it's all about these positive and negative areas. That's the key. So for instance, I got a little worksheet for us, if I can find them. I want to take a look at this together. Oh, well, I'm gonna hand these out to you. We need to do a little work first. There's a big leap we have to make, because you're gonna look at this, and if you haven't had calculus, you're gonna go, what in the hell is written on that page? And by the end of today, you will know what the hell is written on that page. And maybe if you've had calc before, you'll have a deeper understanding. those beautiful symbols on that page. Thank you. Cool. So we'll get to that in a minute. We actually, the page that you have on top, we're probably gonna do that second, because we have to do the one behind it first and talk about, no new homework will come today. We got a lot of shit to get under the bridge. We gotta let it flow under the bridge. So this whole process of finding those precise areas is what I wanna get us understanding today. So this was all approximations. This web work problem, that's an approximation. You need infinitely many rectangles in general to get the truth. So how do we do that? To get the precise net area, we need calculus. And in particular, some stuff you might have never seen before, but something you definitely saw before, which is limits. So I'm gonna put this up here. Sums, products, and limits. And I'm gonna do a really beautiful example for you. It's like my favorite example to talk about in calc class. So let's do this. Example. Find the precise area between, we're gonna go with an old, easy on the mind friend, y equals x squared. Now moving away from time. This isn't always about time and velocity. We're moving away from that. Y equals x squared, the x-axis, and x equals 1. So let's draw a picture. Parabola, horizontal line, and a vertical line. Here's x, here's y equals x squared, here is 1, and here is my parabola. So that guy right there is 1 squared, so it also ends at 1. And this is the region I want to find the area. That's what I'm trying to describe there. Looks like a triangle. It's less than half that square that I've made here, so I can make an estimate. It's less than a half. That's not helpful. How much less than a half? What exactly is that area? How much paint do I need to buy to paint that sucker? So what we're gonna do is a process called definite integration. Is needed. This will probably be the heaviest thing we've done all semester. It's elegant and simple, but putting the ideas together is a whole other thing. I will not ask you to do this too much. Probably in class while we're safely, you got your student driver, I got a break, everything's cool, nothing bad can happen to anybody. Definite integration. So what is this? Question mark. Step 1. Cut your horizontal interval. Here, in general, that would be A to B. For us, it's 0 to 1. The x values run from 0 to 1. And we're gonna do that rectangle game like we've been doing, but we're gonna do it in a cooler way than we've ever done it. Step 2, partition. These are technical words. I'm not just picking fancy words. Partition the interval into n sub-intervals. And this n is an arbitrary number. These subintervals don't have to be equal, but we're gonna make them equal just because it makes life easier. So for example, if I said n equals 3 over here, you would make 2 cuts. You would say, okay, here's one of them, and then I'm gonna show you, they could be very different sizes. Here's the second one, and then here's the third one. Cut, cut, and I got that piece left. So these are called subintervals, and the process of making these little cuts is called partitioning the interval. This is a partition of that interval. Here's a different one. I mark it at 1/3, I mark it at 2/3, and these are all equal. So there's a different partition where they're all the same width. Doesn't matter how I do it. That's the amazing part about this. But what we're gonna do is we're gonna pretend for us, let's use equal size intervals, size cuts. Let's just say that. Let me get my picture back and try to fix it at the same time. I saw when I went through the back, I could see how crooked that mofo was. All right, there we go. So I'm gonna cut that into n equal pieces. So if I do that, the first cut is 1 over n. Think about it, if I had 100 pieces, if I cut the interval 0 to 1 into 100 pieces, it would be 0, 1 100th, 2 100ths, 3 100ths, on up, until I got to 100 100ths, which is 1. So we have to do this in general now. So this is 1 over n. What's the next one? 2 over n. It's 2 of these. And then, what next, Sam?
3 over n.
Thank you, sir. 3 over n, and 4 over n, and 5 over n. And obviously, if I keep going at this thing, I'm gonna go way past that. But put a dot, 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 and then we'll pick it up right before this one. And this is the part that's gonna stretch your mind a little bit, the notation here. So remember that this was 1, and that is equal to n over n. So what's this 1 right in front of it? It's what over n?
N minus 1 over n?
Yeah, beautiful, Leo. N minus 1 over n. So for example, if n is 100, and I go dot, 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 and I come out here, and here's the 1, the cut right before that is 99 100ths. And this was 100 100ths. It's just that same fraction backwards. So these are gonna be my subintervals. Then to make life easy, now, what I need to do, sorry, before I tell you how I'm gonna make my life easy. Remember how we used either the left endpoint or the midpoint or the right point to make our rectangles? Think about the difference. Here's a left endpoint rectangle on there. Here's a midpoint rectangle on there. And then the right endpoint rectangle looks like this. I'm going to set this up so that it doesn't matter where we pick. In fact, you can pick any point you want inside these guys. So what we're going to do next, step 3, is in each of these subintervals, pick a representative point. So for this first one here, I would call it, well, let me write it out and then do it. 3. In each of the n, excuse me, subintervals, choose a single point that represents everybody in there. Choose a single representative. And let me clarify on the top right of the board, what do I mean by that? So here's some fancy notation. Don't get hung up on it. It's just looking different to keep our brains straight. So, e.g., in the ith, that is a letter I with a th. That could be first, second, third, fourth, fifth, sixth, It doesn't cover the ND or the RD for third and second, but this is the I. This just means subinterval I. Subinterval I. So this is subinterval 1. This is subinterval 2, 3, 4. What subinterval is this guy? This last one. If this is the first, the second, the third, which one is this? Here's I equals 1, I equals 2, I equals 3. What does I equal in there? For the rhythm.
N minus 1.
So which, did I use the left endpoint to figure out where I was? Notice how the first subinterval has a 1 on the top here.
Okay, so 1.
1. Well,
1.
nth.
Okay.
Does that make sense?
Yeah.
You see that this last one, this is the nth subinterval.
So in the case of 100, if you're breaking into 100 pieces, it'd be 100.
This is the 100, yeah. So this is the first subinterval, the second, this is the third, fourth, fifth, sixth, seventh, eighth, this is the 100th subinterval. And the I, the letter I, just represents where I'm at in there. So if I said, hey, go to the I equals 75th subinterval, you're just gonna count over 75 and get to that one. And what's its right endpoint gonna be? What's 75 100ths, the way I'm counting this, yeah? What's this left endpoint? 74 100ths, yes. Let me stop. Any of this need clarification? Any questions? Is it feeling okay? All right. Okay, good stuff. So I'm going to go to the ith, an arbitrary subinterval, the ith one from the left. Choose representative, and it's going to say x sub I, so x sub 1 for the first subinterval, x sub 2 for the second, and I'm going to put a little star, so like an asterisk there, just for notation, so I know what that represents. This means this represents the whole subinterval. So over here, if I picked one, this would be x1 star. And then if I picked a different one in here, this would be x2 star on down the way. So let's review really quick. Cut your interval into n pieces. Equal or not, doesn't matter. In each one of those, pick your favorite character. Pick your favorite number out of each one that'll represent everybody in that cut. We're going to choose them. Then, step 4. Let delta x sub I, so that's a capital Greek letter delta, it's just a triangle. If you've done a lot of science, you've seen that number for change. We've seen it here, right, for derivatives. We talked, yeah, we did, yes, we talked about derivatives. It feels like a long time ago, but we talked about derivatives in here. So that's just change in x. And this is equal to the width of the ith subinterval. This is the base width of our triangle. Our rectangle, excuse me. A rectangle above that subinterval. I don't know if I'm hyphenating that. I don't think I have that. So this, whatever this is, this delta here, so delta x1 for us is 1 over n. What's delta x2? How wide is this? It's just 1 over n. There we go. Yes, yes. They're all 1 over n, right? In this case, so delta x1 here is 1 over n. Delta x3 is 1 over n. All these guys are the same width. So let's actually make a note over here. These can be all the same if we make equal cuts. And in fact, if the cuts are all equal, if all cuts are equal, we know exactly how wide those are gonna be. Equal. Delta xi equals the width of your original subinterval, which is the right endpoint minus the left endpoint, divided by the number of cuts. So that's right end of interval minus left end of interval. Like, and this tells you how wide your interval is. And then cut it into equal pieces over number of cuts. A lot of notation going on here. And I'm gonna like put this all up and then we're gonna go through and do it for this guy. So let's just get the whole plan up here. Step 5, compute the Riemann sum for our arbitrary n. This part is where it's gonna take, we're gonna have to grow a little to get better at this. And we're gonna practice today doing that. For our arbitrary number of cuts, n. Put a colon there, because what that's gonna look like is this. It's gonna be the height of your function at the first representative. So your function, let's hear, I'm sorry, I should have said this. Assume f of x is our function. It's going to be the height of the function at the first representative times the width of that interval. Let's draw a picture underneath, and that should say sub 1, excuse me. So this is height of first rectangle. This is the width of the first rectangle. And we know that's how you get the area, right? Base times height. We've been doing that shit for, well, a little over a day. Not that long. And that should be the word rectangle. Plus the area of the second rectangle. What is the height of that rectangle? It depends on what I chose here. Times the width of that rectangle, which may or may not be the same as that. So this is area of second rectangle. And I keep doing this. So the third rectangle is that high times that wide. Plus, blop, 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 put an ellipsis, 3 dots, plus the last one, which is f, whatever that last representative is, the nth one, times the width of that last interval. This is called a Riemann sum. This stuff's a little over 100 years old, like 150 years old, maybe something like that. It's pretty new, math-wise. What I want to talk about next is how to make this pretty. So we need to talk about some notation that if you're going to be in Calc 2, and you already are registered for my Calc 2 class, not registered yet, but will be. I know of at least 3 people I'll see next spring. You're gonna need this notation. So I'll come back to this picture. I can easily reproduce that. But I do wanna leave those steps up for us. So, notation. And in fact, let's put above it summation notation. How do you compactly write big sums of things? If you ever wanted to take there's a math exam called the Putnam exam. Very challenging exam. Most people score no points on it. You score 1 point, you're like super genius. Sometimes we have people score points on it. You need to know this stuff. So summation notation. If I have a list of numbers added together, A1 plus A2 plus A3 plus, let's just do a nice simple one, plus A4 plus A5. Got 5 things added together. I don't know what they are. But it's a variable plus a variable plus a variable. There's 5 potentially different things I'm adding together. To compactly write this, so compact notation would be this. I write a capital Greek sigma. Now sometimes people's sigmas, when they start writing them, look freaking weird. Sigmas don't look like this. They don't look like that. They're not like gonna eat some. They're not like Jaws, like a shark gonna eat some. They have nice flat tops, flat bottoms, parallel, little dent in the middle. If you looked at it this way, it'd look like an M. And then this little tiny tails on there, but you don't need that. If you even did that, that's a beautiful sigma. I just get a little fancy with it. So this is called the sum sign, or summation sign. And again, that is a capital sigma. If you ever end up doing stats, or you have that stats, that's the lowercase sigma for standard deviation. And then here I have a thing called an index. So this is called my index. And it's going to start at some value. This one starts at 1. So this is the start value. And on top, I have the end value. So notice here, I've got this little moving piece. It goes 1, 2, 3, 4, 5, starts at 1, ends at 5. So this is my end value for my index. And then to the right of that, I look and see what is changing here. And what I'm doing is I'm adding together a bunch of A's that have subscripts that run from 1 to 5. So this thing right here that I've written is a compact way to write that. We're gonna practice this a little bit, because we really should, for lots of reasons. Let's see, I think I can kind of reproduce that part again too. Okay, so let's practice. What if I had A3 to the 5th plus A4 to the 5th plus A5 to the 5th plus A6 to the 5th plus blah, 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 out to A sub 99 to the 5th. So the first thing I ask myself is, what is constant, what doesn't change, and what does change? So the part that doesn't change is that, right? That pattern is common to every part of the sum. What does change is the number at the bottom. So I'm gonna put a variable down there because I know this changes. And I wanna add up when that's 3 and plus when that's 4, all the way up to 99. So I put a sum out in front, sum. I read this as sum of these things. What do you think I should start at? 3. All right. Do we see that? The first index is 3. So I start at 3, where do I end?
99.
Beautiful. And that sure beats writing out all that stuff. Let me ask you this. Let's go the reverse process. I'm gonna give you something that I'd like you to tell me what the sum looks like. And be sure, please use some ellipses if you need to. So convert the following sum. The index doesn't always have to be I, so let's play a little bit. J equals 3 to 7 of j to the j plus 1. Okay, I'm kind of like jumped in there. It just kind of had to be a jump. So look at the first one. What does this expression look like when j is 3? And then what does it look like when it's 4? And put plus signs between those things. So you're literally subbing in the different j values to that expression and writing out it. This one you don't need ellipses for. I made it nice and small. not feeling good about it, we should talk about it. All right? Okay, I'll give you a minute to just sit with that. I guess I'm gonna have to, we just don't have enough board space in here for me to not do this. I wanna practice with another one. So if you keep working on that one, if you're having trouble, I'll come over and give you a hand. But I'd like you to write out this one here. Write out these, because we're gonna need them in a bit. Notice now I've changed the top index. Now that's just n. What do these things look like? Here you will want ... So break these down. You're starting at 1, right? We're definitely starting at 1. So that's the chill part. Wow, things. Ooh, I like that. That's a nice touch. That's a very nice touch, yeah. That's a weird looking sum. You're good. Yeah, perfect. That's a great start. A good plus.
And what's the next value I? It's the plus, oh, for the plus, oh, no. So if I wanted, and I would put that in, it's literally just the index. So it just says write an item, what's the next item? Yes. What's the next one? There we go. Yeah, just like that. What are we doing here? What are we doing?
It can, but where does this end? Because right now you got an infinite sum, which is super cool, but not quite. There you go.
Yeah.
There you go. What's the little subscripts in your mind? Like, what are the subscripts? Because I think I see what you mean.
Yeah. So what are I values? First one is what? 1. What's the second one? Yeah. So this just means first value 1 plus 2 plus 3. So you don't need the fanciness. It's actually much simpler. It's the things you've got as subscripts. It's just 1 plus 2 plus 3.
You know what's your last thing you're gonna plus? What is that?
Well, what is that letter? Yeah. So plus, let's put that.
Yeah, man.
Does that make sense?
Yes, yes, you were making it way too hard. You're getting very fancy, which was cool. It was cool fanciness. Got a lot of fun on this. Oh yeah. Oh shit. Oh, I can't even keep you employed. I gotta like keep giving you extra work here. Jeez. All right. Oh yeah, I already looked at yours. So beautiful, except we just need pluses instead of commas. And that's the only difference. Other than that, it's perfect. Yeah. Make sense? Cool. How you doing, Sam? So, lovely. Yes, ma'am. Yes, good shit, my friends. So, we've talked about this dude before, Euler. If you're in Calc 2 with me, you're gonna get some really crazy Euler shit. But Euler was like doing math, like his mom like gave birth to him, the doctor slapped his ass and he started speaking math. Just like talking math. In grade school, one of Euler's teachers gave to the class, add those all up. And Euler, so quick, looked at that and said, oh, that's 50-50, 5,050. His teacher's like, whoa, wait a minute. They didn't have calculators, right? This is pre-calculator. How did you know that was 5,050? And Euler's like, well, okay, so if this is my sum, I can also write it backwards. So Euler's like, okay, let's write it backwards. And line things up. And then what would be underneath this guy? Or 2, and then 1, yeah? So wrote it sum backwards, and then says, okay, okay, so I'm gonna add down. The s plus s is twice the sum. What's the sum here of these two? 101. What's the sum of these two? Plus 101, plus 101, plus 101. Well, that's pretty sweet. How many 101s are there? How many of those? There's 100 of them. So Euler said, well, wait, then like all this is like instant. Euler said twice the sum of those things is 101 times 100. So the sum, if I just divide both sides by 2, is 101 times 50. And that is 50-50. Pretty cool, really cool. So this actually has a beautiful thing called a closed form. And we can kind of do it this way. I'm gonna show you this one. This one's like, we're not gonna do that one. But if I asked you to add the numbers between, so everybody got this. We know this is 1 plus 2 plus 3 up to n. Let's look at that over here. So if my sum is 1 plus 2 plus 3 plus, let's do this. What comes right before 100? 99. I'm gonna do it again. The sum is also 100. Oh, sorry. I meant n. We already did this thing, right? Plus n. What's right before n? N minus 1 is right before there. So now let's write the sum backwards. It's put the n down here, plus the n minus 1. What would be the next thing? N minus 2 plus, and then what's under here? 2 and 1. So twice s is, what do those two add up to? N plus 1. What do these add up to? N plus 1, 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 n plus 1. How many times? Careful. N times.
Yeah, n times.
N times. If n was 100, definitely 100. So there's I almost did it. There's n of those. So 2s is n times n plus 1. And so the sum is this. And this you should write down. Is the answer, this is n times n plus 1 over 2. Anybody asked you to add up? Somebody says, hey, find the sum. 1 plus 2 plus 1,000. You hear people clicking, you know they're suffering. They're literally typing this shit into their calculator. You don't need that. What's n? What is the n in this sum? 1,000. So the sum is 1,000 times 1,001 over 2. And work that out. Who knows what it is? It's something like 5,050, but bigger. Amazing. This formula is going to come in handy, but this one's going to come in more handy today, probably. If you wanted to add up, well, first off, let's talk about what this is. This is 1 squared plus 2 squared plus 3 squared plus n squared. Everybody cool on this? I didn't get to check everybody, just wanna make sure we're good. Yep, awesome. So this is called the closed form. It's the formula for computing the sum. This one is n times n plus 1 times 2n plus 1 over 6. And good luck working that one. That's weird. But how would I use it? If I asked you to find 1 squared plus 2 squared plus 3 squared plus 30 squared? You wouldn't do that. Well, you might. If you had a lot of spare time and forgot about everything we've talked about. So what's n here? 30. It's the last term, right? It's the very last thing I add on. So n equals 30, so this sum is equal to 30 times 31 times 2 times 30, which is 60, plus 1, all over 6. Who cares? we get our calculator out, we do that instant. So these formulas are just absolutely beautiful. And we're going to use them like crazy. I got a quick question for you. Here's puzzle time. That's right, mini math club. How could I possibly find this sum? And it just take a minute. 11 squared plus 12 squared plus up to 20 squared. Take a minute, don't say it out loud. How can we use what we've talked about today to find that? It's not starting at 1, so just raw application of the formula ain't gonna cut it. And then if you think you got it, could you actually find the sum for us with a calculator? Or, long multiplication, either way. Man with an answer. Oh, I don't know what the actual, yeah, let me see.
Yeah.
Yes. Yes. You got something, Leo?
Yeah.
What you think?
Yes, this is true.
Yeah, I know, but,
Yeah.
I know.
Okay.
Yeah.
Yeah.
Yeah, no,
You're
I'm
right.
trying to think of because
I don't doubt Desmos.
Yeah.
Let's not spend too long on this. Someone tell us how to work this through. Kyla, do you got something for this? Like, what was your method?
I just did the n equals 20 and did the formula minus n equals whatever, subtracted.
Yeah, so we only know how to do from 1 up to something. So notice that this is 1 squared plus 2 squared plus 3 squared all the way up to plus 20 squared minus 1 squared plus 2 squared plus 3 squared up to 10 squared. You just subtract off those first 10 terms. Does that make sense? And when you do that, what you're left with is starting at 11. You're like cutting out this guy, because this guy goes like up to 10 squared, and then he goes 11 squared, 12 squared, up to 20 squared. So you're gonna use the only tools you have, which add up from 1 to something, and subtract those. So this is going to be, up here, this is the n equals 20. This is the n equals 10 version of that formula. So when you have the n equals 20, it's 20 times 20 plus 1 times 2 times 20 plus 1 over 6. This is for n equals 20. And then minus the 10 version. 10 times 10 plus 1 times 2 times 10 plus 1 over 6. And I think it was 2485? Yeah, if you got it right. Yeah. So, okay, we're not, like, we won't do much of that. I just wanted to play with it a little bit. Cool. Any questions and things? Sam, you're good on this?
Yeah.
Okay.
I learned to next week.
Oh, did you? Oh, nice. That's awesome. Cool. Very good. You seemed like you had some insight into it. Okay, so let me see. That was what was the last step I had when I was numbering steps? Was that 4? 5. Okay. Cool. 6. 6 is next. So back to the steps. Back to step 6. Let me see what else I wrote just real quick, Sam, just to make sure. Yeah, cool. Step 5, because I want to use our notation. Let's finish up step 5. We had the Riemann sum that looked like this. It was our function at the first representative times the first base width. That's a 1. So that's height times base plus height at the second point times the base of the second rectangle plus all the way up to f at x sub n star delta x sub n. This is the nth rectangle. It's the area. These are just areas we're adding up. Signed areas. They could be negative. If f is negative, the area is negative. So let's use notation. So compactly, this is the sum as I goes, look what's moving. This little index, it goes from 1 to 2 all the way up to n. So I'm going to start it at 1, I'm going to end it at n. And then I have whatever my function is at x sub I star delta x sub I. This guy right here is the approximate area. Approximate signed area. But it's approximate. We don't want approximate, we want the truth. And that's when step 6, our final step, comes in. Let n go to infinity in your step 5 formula. Exclamation point, because I'm stoked, because I'm about to write something here. So it's limit as n goes to infinity of the sum I equals 1 to n. It's that thing I'm writing up there. I'm just writing that Riemann sum again. And that is the precise area. And it's so important that it has a symbol name. This process, the getting to here, so if this limit exists, I'm gonna put it equals. If the limit exists, and it's going to exist for everything we'll ever do in this class. There's no worries. When you go to grad school in math, Then you worry about when it doesn't, but for us, it does. If the limit exists, we write, so this equals is you write, the sum sign and the limit combine into an elongated S, standing for sum. But it's a fancy sum. At the lower end is the left endpoint of the interval. So this is left interval, or the start of my interval. Remember, my interval was A to B. And at the top, I write a B. So this little a is right next to the bottom of the S. The top, the B is right across from the top of the S. This function, f, I write again, but these guys just become x's. So this x sub I star just becomes a normal x. The delta x, just like when the derivatives when we did the limit on the delta y over delta x, it became a dx. So in the limit of these things, as they shrink to nothingness, it becomes a dx. So let's talk about this. Let's get some verbiage for this. This is called the definite integral of f of x from x equals a to x equals b. And this means everything we just talked about for the last hour. So this is a process. But the good news is it's not going to always be a process. It's going to be a much prettier and easier on the hand and eyes and mind and heart process. So that is the definite integral. So this thing right here, this is called the integral sign. Let's get a little lay of the land. The integral sign. This thing right here, this f of x, is called the integrand, the thing I'm integrating, integrand. The a and b are called the limits of integration. And this little d whatever, this is mostly letting you know what your variable is, and it kind of is a cap. It just kind of like blocks this off, but it's called the differential. We got about 10 minutes. Let's do a little bit with this. And let me show you how this is actually, let me write something that's going to make life a little easier, and then we'll do one of their problems. So, shit, what was I gonna do with this? Yes, so this is interpreted as the signed area between the graph of f of x, y equals f of x, between x equals a and x equals b. So in other words, if I have a function that looks like this, I'm just making it look funky. Give yours just a little bit of negative. It doesn't have to look just like what I've done. Let's say that this is A, and this is B, and this is my function, f of x. Then what this represents, get out of Jasmine's way here, this is the area 1, so it's this A1, plus this A2, plus this A3 that ends at B. is A1 plus A2 plus A3. It's the net signed area between A and B on the x-axis. With that in mind, check out the activity 432 sheet. It's the one with the graph on it. We are going to learn what's called integral calculus. We've been studying differential calculus, derivatives and how to find them. We're going to study integral calculus and how to find these things without doing all this craziness. It's going to turn into a beautiful thing. But for now, this gets us really far. So look at that sheet. It says, find this. It says, find that. So I read this as the integral of 3x from 0 to 1. I'm just going to write that out here. The integral, and you could say the definite integral. The definite integral of 3x from 0 to 1. The limits, the integrand, and the definite integral is that whole thing. It tells me how to interpret this. So I'm going to go look at my function. That's y equals 3x. That's a good old line. So there's y equals 3x. And I'm interested in the x-axis between x equals 0, where it touches the origin, to x equals 1. So I just want this area right here. That area of that right triangle is the answer. What is that area? 3 halves. Because it's at x equals 1, this has height 3. The base is 1. It's just a triangle, right? So the area is 1/2 base times height equals 1/2 times 1 times 3, 3 halves. And that is what that is equal to. It is really important for you to have an understanding of this as the signed area. Could you do me a favor and look at the second one? And then we'll call it a day. Could you do B, please? You're going to want to graph out y equals 2 minus 2x. Wednesday, we're going to keep up with this because I never did find the area that I wanted to find it, but I'm going to come back on Wednesday and do it for you because it's too beautiful not to. We'll probably just keep practicing this stuff on Wednesday, pushing it forward. Six, good Lord. 1, 2. Make sure your graph looks like that, or let me know if my graph's wrong, but I'm seeing some strong nods. So what I would recommend is looking at the total signed area once you get that area and that area. One is positive, one is negative. What is the net? Probably need to find that point right there. Well, I think my graph is pretty shitty. What is that x coordinate? Should be one, right? Yeah, should be one, so right now I'm gonna cheese it out. Okay, sorry. That A2 is a negative area, right, because it's under the x-axis. Let's see. What is A1? Is that just 4? Because it's got a base of 2 and a height of 4. It's 1/2 base times height for a triangle. And then this guy runs from 1. Wait, how is 3 across? Is that right? 3, and then how deep are we? 6. So what's A2? -9. 18 is the base times height. -18, excuse me. I'll put a -6 there and make that clear. And then you take half of that, -9. You should get -5. We're gonna learn how to do this by Friday with no pictures. I think. It's Friday or Monday. We only have 4 weeks left. I wanted to turn off the recording before I said something. Never mind, dear viewer. This isn't information you care about.